Thank you very much. It's really a pleasure being here. So I'm going to be talking about this some projective duality statement, which is classical theory, but for some Kummerfourfolds, which are some Hyperk manifolds of dimension 4. So we actually start with a theorem by Ortega and Nguyen around 2005, which says that the Cobol cubic C3 inside some pH dual and the sextic, which is some sextic inside P8, are projective dual. And starting from this theorem, today we're gonna focus on some Kummerfourfolds. Of some principally polarized abelian surface. And we're gonna say that Kummerfourfolds of these surfaces have two birational models. Which are projective dual. So I'm going to first revise this theorem by Ortega and Nguyen, and then I'm going to introduce the Kummerfourfolds and explain how this theorem can prove such a statement here. Before I dive into the mathematics, let me tell you that this is a joint work with 3 other people. And these are Daniele Agostini, Pietro Beri, and Angel David Rios-Ortiz. Okay, so we're going to start on some basic facts on abelian surfaces. So I start actually with the curve of genus 2. And I consider then, so the peak naught of the curve. So this is going to be my A. So it's an abelian surface. And actually with the curve C, I can also consider the Jacobian. So it's going to be J, and it's just the peak 1 of the curve. And we have a natural action of the abelian surface on peak 1 just by tensoring. And this is going to be a torsor on A. But if this is just a torsor, this is another important feature. So there's a map from the curve C to peak 1 just by mapping a point to the degree 1 line bundle OCP. And this turns out actually to be an embedding. I call theta the image of the embedding. And theta as a divisor on J is a principal polarization. Meaning that theta square is equal to 2, or equivalently by an application of Riemann-Roch is just saying that the global section of theta are just one-dimensional. And there's actually another feature that is going to play a role in this talk, and is that here we have the negation, which is an involution. with the 16 points which corresponds to the two torsion of the abelian surface. And here we have an involution called tau that maps any degree 1 line bundle to the tensor product of the canonical tensor, the inverse of L. And you see the canonical bundle has degree 2. So this means this is again a degree 1 line bundle. And actually, so here on C, I have also the hyperelliptic involution. And if you think about the very definition of this map here, so this map here is going to be equivariant. And the hyperelliptic involution has 6 fixed points, which corresponds to the 6 ramification points of the 2-to-1 cover of P1. And if you choose a point of this, so these are called Weierstrass points, if you choose a point C for the identification between A and the torsor, then also the inverse and tau are going to correspond. So choosing a Weierstrass point for the identification of A and C identifies the negation on A with the involution tau. So actually, to be more correct, I should carry on this distinction between A and J for the entire talk, but actually I'm going to ignore this and pretend that I'm choosing a Weierstrass point and then I'm identifying the two.
For what? For identification of C on this image? Or?
Sorry, of A, sorry, thank you. So for A and J, so the abelian surface with just with the translation by Weierstrass points. Thank you so much. Yeah. Okay. And now I would like to tell you something about the embeddings of the surface. We saw that, so on my abelian surface, I have my divisor of theta, which has no sections. So this is not going to give me any interesting projective embedding. So I just consider now twice the polarization. So this goes from A to theta dual. This is isomorphic to P3. And the fact this is base point free, it factors through the quotient by the negation. And an embedding. So here I have A over plus minus 1, and then it's followed by an embedding here. And then here, so this is about twice the polarization, but again more interesting is what happens if you take 3 times the polarization. And here comes the theorem of Kobold, 1917, and which was revisited by Bouville and improved by Bouville in 2003. And says that so the linear system given by 3 times the polarization is an embedding and yeah, and there exists a unique cubic C3 inside PH dual, such that the singular locus of the cubic contains the abelian surface. And actually, so if A is general, then we have actually an equality. And there's another thing which I'm going to tell you later. And yeah, and so this C3 is actually the cobble cubic which I had there. Okay. So now we turn out about equations. So we have seen that we have some projective embeddings, some projective models of our surfaces, and we would like to understand better the equation defining this projective embedding. And for this, we need the help of the theta groups given by due to manifold. So in the 60s. Yeah.
So this Kummer cubic doesn't depend on A. It's the same for all abelian variants.
Sorry, what's that?
It means that this depends on okay, the cubic depends on A.
Ah, the cubic, yeah, no, the cubic depends on A. But for any A, you choose any principally polarized abelian surface, you take the linear system free theta, and then the image, so here is the image of A along this embedding, you find the unit cubic here. Yes, so theta groups of theta. So we have to consider line bundles on the abelian surface. And then we consider the set of linearization. So GL. And this is going to be a set of A, comma phi in A cross C star, such that the translation of such that phi is an isomorphism from L to TA star L. And this is a group, there's a structure of a group, but the group is not the direct product of the two. So for the structure of the group, we have to define this way. Sorry, A comma phi composed with B comma psi, defined as, so I have my L and my phi. And what I can do, I can take psi, but before I have to apply the T upper star beta, and then I apply T upper star beta B here and also here. So the composition is going to be the composition of these two, the linearization that I need from L to the translation by A and beta, plus beta. And this, in turns, gives me okay. And so the nice thing about this is that, okay, now I'm gonna write just the theorem for our interesting polarization, so for our interesting line bundle. So if L is equal 3 times the principal polarization. Then GL sits in this diagram. Sorry, G 3 theta sits in this diagram. So here I have A3, and here I have C star. And I have an embedding of this inside the GL of the linear group of global section of 3 theta on A. And here I go to the PGL. And here I have C star. So in other words, it's telling me that I have a natural action of this group, or better on the projectivization of the group, on the P8. And so with this action, we can complete actually the theorem here. So here I have the action of A3, so the free torsion points of my abelian surface. And the thing is that phi theta is equivariant for the action of A3.
Can you show the other manifold?
Yes, just a second. And also the cubic. Yeah, I'm gonna send this blackboard up away. No? Okay. So we have produced our theta groups GL, and then we have seen that this G free theta, the theta group associated to free theta, as the projectivization is A3, the free torsion points, and the free torsion points act linearly on the projective embedding, so on P8. And everything is equivariant, so we have that the Cobol cubic is unique, but is also equivariant, is invariant by the action of A3. Okay, so this was, and also this representation here is standard in a sense that G free theta is isomorphic to the Heisenberg group. And H0 of free theta is the Schrödinger representation. So with these two lines in the end, I just want to say that the action is pretty explicit, and you can actually use the action to write down the explicit Cobol cubic with explicit coefficients. And over here you have the Kummer quartic. Okay, so this is what I wanted to say about abelian surfaces. And now we move on to Kummerfourfolds. So and so the first thing is I want to define this thing. So let's A be any abelian surface. We consider then the Hilbert scheme of n plus 1 points on the abelian surface, and with the Albanese map. It goes to A, and it factors through the Hilbert-Chow morphism, so to the symmetric product of the abelian surface, and the summation map here. And I consider here the kernel or the preimage of the Albanese map, and I define this to be my Kummer and fold. So this is the Kummer n-fold. And so the properties of this variety here is that cum NA is a Hyperk manifold. So of dimension 2n. And so Hyperk means just that it is simply connected. Plus I have a symplectic form, which is everywhere non-degenerate. Okay, so this example here of a Hyperk manifold is due to Beauville. And was one of the first example of Hyperk manifolds. And so there are many properties which this Hyperk manifold enjoys. And and one of these is that resembles to the K-free surfaces and also to abelian surfaces. And one property is that we have that the H2 of cum n of A with integral coefficients is isomorphic to the H2 of the abelian surface. And direct sum with an extra class which I call delta. And this is an isomorphism of lattices and also of integral Hodge structures. So what are the lattice structures on the both sides? So here I have the intersection form. And I declare this to be orthogonal and that the square of delta is equal to minus 2n plus 1. And delta is the half of the exceptional divisor of the Hilbert-Chow morphism, which I had there. And on the other side here, I have what is called the Beauville-Bogomolov form, Beauville-Bogomolov-Fujiki form. Okay, so one of the motivation for this project was to take up this challenge here. And the challenge is find a projective, locally complete family of Kummer n-folds. You see that this is a kind of a difficult task. So there's no example known of such a projective locally complete family of Kummer n-fold. And the difficult part from our perspective in this case is that the deformation of the Kummer n-fold are one more. So the Kummer n-fold deforms in one direction more than the abelian surface. So if we want to find a locally complete family, we need to lose the abelian surface, and we need to lose the thing. But there's a hope for this, and the hope is that nonetheless, usually the moduli spaces of Kummer n-folds are irrational, known to be irrational for a large degree. And we know that the moduli space of Kummerfourfolds with some discrete invariants, which are the Beauville-Bogomolov square and the divisibility, this is known to be irrational. And this means that we can expect to find a locally complete projective family of such Kummerfourfolds with these invariants. Okay, so I think I'm gonna need the blackboard down there again. I can do just once at a time. So it's a nice moment for questions if you have.
So can you explain again what the rationality has to do
Okay, so if you, where is it going? Oh yeah. So if we want to find the locally complete family, so an example of hyperk manifolds is for K32 type is the final variety of lines of cubic fourfolds. And the fact that you can find the representation of, that you can find this family is basically that's one of the moral reasons that the moduli, the space of the cubic fourfolds are parameterized by some open sets of P55, so the cubics in P5, and this is a rational space. So you can really write down so the base of the family, and the base of the family has a nice geometry which is easier to understand. I think this is kind of the explanation. Okay, so the thing I'm erasing now, I was telling you that the Kummerfourfolds of abelian, of principally polarized abelian surfaces have two projective models. So now we are interested in, so we take some principally polarized abelian surface, and we look at the inside the Rencontres of my fourfold. I have two generators. So one is theta, and the other one is minus delta. And we can compute that the NF cone has these two extreme array. So this is my NF cone, and is equal to the movable cone. And now, so we want to understand what are the linear systems related to these two extreme arrays. Okay. Yes, I can tell you more about this. So I can tell you that the Bouville-Bogomolov square of theta and of 2 theta minus delta is equal to, and the divisibility of theta is 1, whereas the divisibility of 2 theta minus delta is equal to.
So you are taking very general something.
Yes, sorry, thank you. Let a very general. Thank you. Okay. And so what are these two rays? So a multiple of this is going to give me, for sure, the Hilbert-Chow contractions. But actually, that's this theorem by Vladimiro Benedetti, Laurent Manivelle, and Fabio Tanturri, which tells you that sorry. So I think I'm gonna need that to name that isomorphism over there, mu2. So I'm gonna look at as here. So I'm looking at theta and 2 theta minus delta, which are divisor. So this is a divisor on the abelian surface, and I just call this mu2 of theta. So these three people tells you that mu2 of theta is base point 3. And so the map of the map given by the linear systems coincides with this map here to 3 times theta. So this is a phi of mu2 of theta, which is a pH dual, and maps A, B, C to theta A plus theta B plus theta C. So these are the translates of the theta divisor by A, B, and C. And using the theorem of the square, you can see that these guy here is actually linearly equivalent to 3 theta, so it's inside this linear system here. And here we have no dual, sorry. And moreover, so in the second part of their theorem, they prove that we have this, and we also have that phi of theta factors through the Hilbert-Chow. So I'm going to call here K2A. So this is the guy sitting in the Fries symmetric product of A, and an embedding. Okay. And actually, so the other thing that they prove is that the image of this guy sits inside the Cobble sextic. So I'm not going to introduce the Cobble sextics, but the Cobble sextic is out here, and this factor through this, the embedding of the Cobble sextic here. Okay. So now that we have taken into account what happens to the, yeah. I did not define the Cobble sextic. I'm just telling you that there's a nice sextic inside P8, which comes from the moduli space of sheaves on the curve, and this sextic is in there. And so here comes our first theorem. So is Agostini, Beri, myself, and Rios-Ortiz. And we proved that, so we considered the other extreme array, so these 2 theta minus delta, and we proved the following. So first, that phi 2 theta minus delta is base point 3. It contracts the irreducible divisor F, which is defined in this way. So we have subschemes in Q2A such that there exists an A inside the abelian surface such that Z, as seen as a subscheme of A, is contained in a translate of the curve. And you see that this divisor, so I have a map to any such of Z. I can associate the point A, and this map is well defined. And this realizes F as a P1 fibration over F, over A, sorry. Okay. And so the third point of this theorem tells me about the divisor, so the embedding that I have. And it factors through in this way. So we have Q2A. I have my base point 3 morphism given by 2 theta minus delta. And here I have the contraction of F. I call the image of this contraction just N. And here we have an embedding. So I know for sure that a multiple of 2 theta minus delta gives me just the contraction of F. So this is the morphism where it's an isomorphism outside F, and the only thing it does is contracts F to A. And what we prove is that no multiple is needed, and then it's followed by such an embedding here. But the last part is that you see that now we have an embedding of the abelian surface inside 2 theta minus delta. And this is, you can compute it again a P8. And I'm going to call this P8 dual. And the thing is that, so if I call this phi bar, so the last point is that phi bar restricted to A coincides with the linear system free theta on A. So let me stress again that this is not 2 theta, but is 2 mu2 theta minus delta. And what I can consider here is that the image of free theta dual given by the linear system free theta on A. And I get that these two gets identified. So the diagram is commutative. Okay. And finally, in the second theorem, we get to the statement about projective duality. So you remember that at the beginning I told you about this result by Ortega and Nguyen, which was telling me about the duality, projective duality of the Cobol cubic and sextic. Now I have told you about the result of Manivel, Benedetti, and Tanturi, which embeds the Hilbert-Chow contraction inside the P8, where the Cobol sextic lives. We had dealt with the other contraction, which embeds, so the other contraction, then after the contraction I get an embedding inside this pH dual, which is identified with this free theta. So inside here lives the Cobol cubic. And now, so the second theorem tells me about this thing. So we have a theorem, again by Agostini, Beri, myself, and Rios-Ortiz. Yeah. So we let D be the Gauss map of the Cobol cubic. We have the following commutative diagram. So here I have Cum2A. I have the Manivel, the Hilbert-Chow contraction to P8, so this is free theta. On the other side, I have phi 2 theta minus delta, and I goes to PH dual. So this is really free theta minus dual, free theta dual. This is the linear system on the abelian surface. I have the, inside here I have my cobble cubic. So here I have the Gauss map associated to the cobble cubic. And here I have for sure the cobble statistics, as I told you before. And so our result is that this diagram commutes. So in particular, okay, so first maybe I write down the statement of projectivity duality for the cobble hypersurfaces is that dC3 is equal C6. This is Nguyen and Ortega. In particular, we show that the phi, that D of n, which is the image of along this map here, is equal to K2A, which is the image of the other embedding given by Manivelle, Tanturi, and Benedetti. Okay? So this was our theorem. And so maybe now I have some time to explain you some details about the proof.
So did you say if D is bidirectional or?
Yes, so these are hypersurfaces. And yeah, actually, so this is a good point. So these two are projective dual, and I can take also the Gauss map of the sextic, and if I apply it to the sextic, I give back the cubic. But there's a problem for our results, which is just in one direction, is that inside here I have the singular locus of the cubic, and here I have the image of the Hilbert-Chow contraction. So if our results tells about this, I can't say anything about the other direction. So if I apply the Gauss map in the other direction, this guy here sitting in the indeterminacy locus of the other Gauss map, so I can apply the other thing. Too bad. Okay. Oh, the definition of the Gauss map is just, so you can take a point here, P, and associate it to the tangent space at the point P at the cubic. So it's a point in P8. So this, you see that this P8 and P8 are dual to each other as really as projective spaces. And for any point in the cobble cubic, you can associate the tangent space of the things. But actually, you can do really define it on the entire P8. You just take the cubic and you take the polar quadrics. So all the derivatives, you differentiate the cubic along all the coordinates you have here. And you associate to any point here to the evaluation of the polar quadric to any point. Yes. And for hypersurfaces, there's this theorem that tells you that taking the dual is, if you take the double dual, then it's the identity. And you see that the indeterminacy locus of the Gauss map is really the singular locus of the hypersurface. I have 5 minutes, right? Okay. So one of the main ingredients that we need to the proof is the theta groups for line bundles on Kummerfourfolds, on Kummer n-folds. And this is a theory of O'Grady. But first, let me start from the point 1 to show that it is base point 3. Okay, so we have this A3, and I can consider the linear map given by phi to theta minus delta on A3. This is going to go to 2 theta minus delta dual. So this is seen as a linear system on A3, and this is actually isomorphic to the linear system 2 theta on the abelian surface, which is P3. And the map is pretty explicit. So you take a point in here, and you map to, you look at this as a subset, the subscheme of the abelian surface A. You apply 2 theta as a map on the A to Z, and then you take the linear span. So in general, this is going to be 3 points, 3 distinct points on the abelian surface. I take the image along this map here, under this map here, and I take the linear span. This is going to be a P2 in general, and so defines me a point in this P3. And inside here, we have the Cum2A. But we know that the map on Cum2A goes to this space here, which is P8. Right. And so by taking restrictions of the of global sections from A3 to Cum2A, I get this map here. And so what we can do is that we have this rational map here composing this. This is F. And one can see that the base locus of F consists of 2 surfaces, irreducible surfaces. The first is given, so when the 3 points here, they do not span a P2. So if are 3 points collinear, and the other thing is that theta minus delta of Z have support on 2 points. You see that the map here, phi to theta, was the quotient by A plus minus 1. So this is going to be the Kummer surface. And the base locus of F contains for sure the base locus of my object of interest. But the other thing is that we can use the action of the theta groups. So we have G, 2 theta minus delta. So this guy here is going to be 2 theta minus delta invariant. And this here is the theta groups, so the set of linearizations, which are deformation invariants for the line bundles on the Kummerfourfolds. So these are not the theta groups that I talked about before, about the abelian surface, but these are O'Grady theta group, and they are deformation invariants linearization. Once you say that this is invariant, then you apply to this guy here, and you see that this thing is going to be empty. And this shows you this is base point 3. And I think I'm done with the time, so I think it's better if I stop here. Thank you.